Today is lecture 34 of this week, which is the last lecture. We'll conclude our discussion on gallium nitride RF devices. So if you recall, in the last 5 lectures we went from the basic working of a gallium nitride RF device, talking about various aspects, fabrication, and also we talked about what's next for gallium nitride electronics. In between we talked about commercial data sheets, commercial devices, and some of the practical issues in gallium nitride HEMT. So today's last lecture will be a discussion on the linearity of these devices from a device perspective. Okay. So over to the whiteboard here. So we are going to talk about linearity in gallium nitride RF transistor, but this is a device perspective because linearity could be very different when you are talking it from the systems or the circuit perspective. Okay. But a good improvement in the linearity of a device helps improve also the linearity in the system. That's a very emerging area of research in the field. However, today we will talk about what aspects of the device are needed to be kept in mind when we are thinking or talking about linearity in gallium nitride transistor. Okay. But before that we need to understand what linearity means. Okay. So what does linearity mean in mathematically speaking, and although it looks mathematical, but it is very simple. If you can express an output as a linear combination of the individual input, then that is a linear system. So if you can see that you have two function x1 and x2, and y1 and y2 that depends on say x1 and x2. If the linear combination of the output is also a function of the linear combination of the input, it is a linear system. Okay. Diode is for instance not a linear system because you can see that there is an exponential dependence of the current on the voltage. So it is not a linear system, you can prove that. Okay. There could be DC offsets, for instance, non-zero initial condition. All these things need to be accounted for when you are talking about linearity, whether linear combination of the input is giving you a linear combination of the output, right. There have been many discussions of linearity also in the analog mixed signal kind of a circuit analysis. Also, for instance, in this particular circuit you can see that the output voltage has a second order dependence, a square dependence on the input voltage. On this voltage the output depends at the square of the input voltage. Okay. So we can call this as a second order linearity of this small is a simple circuit. The output voltage displays second order non-linearity in terms of the input voltage. So whatever input, if your input voltage is a cos wave like cos omega t, then your output will be a function of cos square omega t, and so cos square omega t can be expressed as some function of cos 2 omega t plus minus something, right. So essentially if your omega was say 1 gigahertz, you are going to get an output at 2 gigahertz also. That is a second order harmonic that is coming in there. Okay. So this is a simple circuit to illustrate that this kind of an output that depends non-linearly on the input can give rise to non-linearity. Okay. So in a very simple way, any mathematical relation, for instance output is equal to alpha times input, okay, can be expressed in a Taylor series expansion in a way. Okay. So there is an DC offset term, there is a linear term, this is the linear gain that represents because the output is depending linearly on the input xt. Then there is a second order term, third order term, fourth, fifth, etc., and in many cases the higher order terms are ignored, but up till third order harmonic, these are called harmonics. Up to third order people kind of taking them into account because they can be significant depending on the frequencies and applications. Okay. And you have to understand that alpha 1, alpha 2, alpha 3 they represent the coefficients of this higher order terms, and we will see practically what it means. Okay. Very much in a transistor what it means, and of course this is not only relevant to GaN transistor, it is relevant to all transistor, but we will keep our discussion confined to gallium nitride RF transistors for linearity. Okay. Before we go into that, an important concept to basically appreciate at the beginning is that typically linearity, when we say linearity, it means you need to have your output which is linearly proportional to your input. Okay. So it means that if I plot my output versus input, I should get a straight line. The ratio of the output by input is gain, which means if I plot the gain as a function of input, then it should remain flat. That is your linear system, or that is your linear say amplifier, linear amplifier in our context. So that linearity, the linearity is quantified by many metrics, but linearity typically has a trade off with gain, which means if you want to boost your gain, your linearity kind of has to be compromised to some extent, and similarly if you want to have better linearity, your gain tends to come down, and efficiency of course depends on gain. So efficiency also would be trading off with linearity, we will see that. especially when you discuss about a little bit about power amplifier. If you want to get outstanding linearity, then your efficiency is gonna be on the lower side. So that's a vice versa, the trade off that you have to pay. But here in a pictorial way we will try to understand why linearity and gain trades off. So you can understand that there is a range over which a system is linear. For instance, here I am plotting the output voltage with respect to input voltage. So you can see that this is the linear range, right. So you can see that this is your linear range of linearity, okay. And you can see that there is a slope, the slope has a certain, the slope is your gain, correct, the slope is certain and that is a gain. Now of course your maximum output parameter or a voltage, in this case it could be power, of course the maximum output and the minimum outputs are, there is a limit, so you cannot cross that. So now if you actually reduce this range, suppose this range was something like over some delta V, so over a certain range of delta V you have this linear behavior. Now if you reduce it by say delta V by 2, this is your linear range, your device or your system is linear only here, not beyond that, and you can see that this linear range is very less, it could be say delta V by 2, which means your linearity has reduced, the range of your, the dynamic range of your linearity has reduced by a factor of 2 and your gain has improved by a factor of 2. You can see that because your slope has become steeper. A steeper slope means a higher gain, okay, a steeper slope means higher gain. So what happens is that if you have your output and your input which are fixed, right, then if you have a steeper slope like that, which means your gain is high, then your range is low, correct, this is your range, the linearity range. And if you want to increase that, if you want to increase the range, then your slope will be low. So you can see that you have a large linear window, however your slope is reduced, so your gain has reduced. So that is a very qualitative and simple intuition about the trade off that linearity makes with gain, and gain depends on efficiency, if you recall, efficiency depends on gain. So if you reduce your gain, typically your efficiency also tends to go down, okay, typically. So this concept is really important to understand, this trade off, that is very crucial to appreciating linearity. So now if we understand that, and now if we extrapolate or if you kind of take it to the domain of a transistor, in specifically an RF power transistor, which is going to be used as an RF power amplifier, okay. And because gallium nitride transistors are predominantly used as RF power amplifiers, although they are being increasingly investigated for low noise amplifier switches and so on, but the dominant application is power amplifier. So we are talking about linearity from that point of view. So a power amplifier, like any other amplifier, it has a Q point or a question point. It is the bias condition, what gate voltage and what drain voltage you are going to bias the device at, okay, that is your question point. So you can see that this plot, the first plot here, represents the output current IDS with respect to VGS, which is the input voltage. So this is your classic ID versus VG, the transfer characteristics, and assuming this is an enhancement mode device, so the threshold voltage is 0, you can see that there is a sharp turn on the device, it is a very sharp turn on, and this is linear for this entire range until this point. So this is your entire input voltage or gate voltage range over which the device exhibits linear, very linear gain. So this is the input swing, you can see this is your input voltage swing that you can accommodate such that the gain is flat or the gain is linear, and corresponding to that in the output current you are going to get this waveform on 180 degree out of phase, this is output waveform, and your gain will be excellent because you have a very linear profile, input and output, correct, this is how it is going to be. And if you bias it at the midpoint, this is the middle point, if this is 1 amp you are biasing at half an amp. So if you bias it at the midpoint, then you actually have half a swing up and half a swing down, you have a perfect swing to swing, there is no clipping of the circuit, no of the waveform. So this biasing condition where you are biasing the device at exactly half of the maximum output current is called class A, okay, it is called class A biasing, where your bias point in the gate, okay, is such that you are biasing at exactly half of the maximum output current, the output current, okay, half of, so whatever, exactly half of the output current, whatever gate voltage gives you that, so it is 2 volt, you are going to bias the device at 2 volt, you swing the gate from 2 to 4 and again from 2 to 0, so that is a perfect, and this is the most linear class, you can say the most linear, because it has perfect gain in this range. And you will see that this actually has a theoretical limit of 50% efficiency. Okay. Why? Because the device is always on and the current and voltages are 180 degree out of phase, and simple math can show that it is a 50% maximum 50% efficiency. So, you are gonna lose in efficiency, but you are gonna get very good linearity. So, there are different classes of operation where you can bias the device at say close to pinch off here. In such cases you are going to clip the waveform, you are going to introduce significant non-linearity when you do that, and the price that you are paying in terms of reduced non-linearity helps you boost the efficiency to maybe higher value 70, 78, 80%. Okay. And so that is very important for wireless communication, specifically for handheld gadgets like mobile cell phones or other stuff where you depend on the battery, and the battery's lifetime directly depends on the power added efficiency of the power amplifier, and that is the most power hungry block on the circuit. Okay. So, people tend to bias the devices at higher classes, class C, class J, etc., where you are going to introduce or you are going to get significantly enhanced efficiency at the cost of non-linearity, and people then try to mitigate that non-linearity by using some approaches at the circuit level, such as a pre-distortion block. Okay. People use a pre-distortion block to kind of mitigate or suppress that non-linearity that arises, but the holy grail is that can we address that at the device level, such that although I bias the device at a certain higher class of operation in order to extract better efficiency of 75-80%, still I do not lose out much on the linearity aspect. Okay. So, that is the holy grail of the GaN RF research, one of the holy grails of GaN RF research also, which of course we did not discuss in the last week because I was going to talk about linearity in this lecture anyways last class. So, you can see that in an ideal ID versus this is an ID versus VG curve, you can see, and this is assuming an enhancement mode device, which is not true of gallium nitride HEMT typically. You can see that it is a perfectly linear curve here, and this abrupt changes here, the abrupt turn off, this is a very abrupt abrupt turn on, or you can say turn off, is actually it introduces non-linearity, as you will see. Okay. But you want this to be abrupt in order to make it an ideal kind of a transistor. Okay. If you have this abruptness, you will ensure that your gain remains flat, the gain does not compress or the gain does not expand. You do not want the gain that if you are plotting the gain with respect to say the input power okay, you want the gain to be flat over the range of interest, and then it can decay. So, you do not definitely want that your gain has a compression very soon, like something like that, sorry. You do not want the gain to exhibit significant compression here. So, you do not want the gain to fall off like that. You do not want the gain to also have an expansion like that. Okay. You do not want the gain to increase with the input power, that is called gain expansion, because you want the gain to be flat. Why? Because in today's wireless communication approaches systems, you have digital modulation of the signal. Okay. A lot of very complicated digital modulation schemes where different parts of the signal can carry a different amplitude, and if you essentially this different input power means that your signal has different amplitude, correct. So, if the amplitude of the signal varies and you have a gain expansion, that means your signal is amplified by different amount at different amplitude levels, which is a very bad source of non-linearity. So, you want the gain to be flat, so that no matter what strength your signal is over this range, you amplify by the same amount. Okay. So, that is why you want an abrupt cutoff, you want this abrupt cutoff there. However, this is also counterintuitive, or this is also contrary to what you would want for some other aspect of linearity, which is namely OIP3. I will come to that very soon. Okay. Because that depends on the second derivative of GM, and we will see that if you have an abrupt turn on or turn off like that, the second derivative of GM can be really bad, very high, and a very high second derivative, because if you take a derivative of such a sharp turn on or turn off, you are going to get a spike, and if you take another derivative of that, which is a second derivative of this plot, you are going to get a very high value, and such high values are usually not very good. Okay. You want that, you want the second derivative of the transconductance to be lower, okay. So, some and the requirement of an abrupt turn on could be it could be in opposite direction of what you want. So you need that again, but we cannot exactly control how abruptly it will turn on, because you can see this is a picture of a real device. For a typical 2DG based HEMT, your turn on will always have something like that. This you can see, this is the black one is the the drain current. You can see that this is not as sharp, but this is gradual, okay, but that gradual increase can sometimes lead to grain expansion, which is not desirable, but this gradual turn on can also help mitigate GM double des, which is also useful by the way for linearity. So this is a conflicting requirement. So that is how the device is, and that is how people have to consider while they consider the linearity aspect of the device. But the important thing to understand here is that the drain current that increases, it does not increase linearly with the gate voltage, and that is why when you take a derivative of the drain current, which is a transconductance, you say that the transconductance is a peak. This peak by the way corresponds to peak Ft also, and then after that the transconductance falls off. This is called your GM roll off, and I will see that this is a very significant and critical issue in the linearity of gallium nitride HEMTs from a device perspective, okay. So we will come to all of this again, but what are the different effects of non-linearity? How do we suffer if we have significant non-linearity in a device? The first thing is that you have harmonic distortion. What it means is that if you have a single frequency of say omega, you are gonna get signals at 2 omega, 3 omega, etc. Now if you are using a power amplifier, you are going to transmit signal in that, because the power amplifier comes in the transmitter chain. So you are going to transmit the signal to an antenna to the nearest base station or cell phone tower, and if you are sending certain power in your frequency of interest, it would be very undesirable if you are also losing out power to undesirable or unwanted frequencies like 2 omega, 3 omega. For instance, you are sending signal at say 1.2 gigahertz for your Airtel or Vodafone or Reliance, your whatever carrier you have, you are sending it to the nearest tower. However, you are losing a lot of power in 2.4 gigahertz and 3.6 gigahertz, which are unwanted. You are not going to use them as the actual carrier, you are losing out power. So that is a bad thing, okay. The harmonic distortion, I mean you are losing power in this unwanted, it also come, you will see that there are many other nonlinear parameters of interest, we will come to that. However, harmonic distortion generally means that you are going to have harmonics of the original frequency, which is undesirable in most cases, okay. Then there is, I will discard this, then okay. So of course people can say that you can put a filter and suppress the harmonic, you can always have a filter, but that is not the solution all the time, because you will see that sometimes there could be interferers and they could lead to frequencies, unwanted frequencies which are very close to your desired frequency. So then filters might not be the solution there, okay, and filters are not always easy to implement at everything that you do, and especially when the frequencies are very close to each other, filters may not be working very well, okay. So that is why it is not the best of solution. Then there is something called gain compression. Gain compression happens when at higher signal strength, input signal strength, your gain will reduce, which means if you are on the x axis, if you have the input power and on the y axis you have the output power, okay, then your input power as it increases, the output power also increases until at some point it starts saturating, okay. So what it means is that if you are going to plot the gain, when your input and the output are linearly dependent, your gain is constant, and at this point the gain will start reducing. This is called the gain compression. The gain is reducing because you are losing out power to the third harmonic, for instance, okay, you are losing out power to the third harmonic of the original fundamental frequency. So that is why you are introducing significant nonlinearity there, you are going to compress. So if this gain was suppose 10 dB, suppose this gain was 10 dB, then the point where the gain has come by 1 dB down, which is 9 dB, this is the point where the gain has come, this point is called the 1 dB compression point. You want that 1 dB compression point to be as far away as possible, which means over a large input range you do not exhibit gain compression, or you can have a large window. You want that 1 dB compression point to be as far on the x axis as possible, okay, and at a 1 dB point you define the output power. This is called P sat, the saturated output power, and of course if you come to even more, say 3 dB, you are suppressing, and this is 7 dB gain. So 7 dB gain is 3 dB lower than 10 dB. So at 7 dB point your output power will slightly increase again. So you could have a P sat that is defined at 3 dB gain compression, okay, and this part is linear, okay, this part is linear. So many application might need saturated output power, such as a strategic or military application, but several applications might need you to work in this regime because of linearity concerns. Okay, you want to operate in this regime because of linearity concerns, and that is called back off. Why is it called back off? Because you are backing off from the saturated power. So if you have the 1 dB compression point here, and people might say you are 5 dB back off, which means you are going to go 5 dB and you are going to see that you are going to operate here, which is 5 dB away from the compression point. Okay, so it is called 5 dB back off, 3 dB back off, etc. So you want to operate at back off because you want to exploit the linearity. The disadvantage is that although your gain is very high, your input power is very low, and so your your output power is also going to be very low, correct. So you always have to have these trade offs anyways. But gain compression is a very significant and important linearity issue, okay, because of third order non-linearity, because of losing power to the third harmonic, you are going to compress the gain in the fundamental frequency, and that is precisely what gain compression is all about. Okay. Then I will discard this, and again I will come back to the third point, which is okay. So of course if you have gain compression, people can say that I will use lower signal strength and not worry about, but again in not all applications you can use lower signal strength, you need to use higher signal strength in many situations. So that is not a viable solution all the time, okay. And also this has ramifications on other aspects of the circuit as well, okay. Now intermodulation is the other form of non-linearity, where there are two interfering signals which are close to the desired signal, and if these two interfering signals are going to interfere, they might create products which are called intermodulation products, IM products, okay. For instance, I have an unwanted signal at omega 1, I have an unwanted signal at omega 2 frequency, they will mix and match and create a lot of unwanted products at different frequency. You will have 2 omega 1 plus minus omega 2, 2 omega 2 plus minus omega 1. These are the frequencies at which you are going to get signals also, and it turns out that some of these signals can be very close or almost identical to the desired signal of omega naught. You will see an example, and then what happens is that you cannot use filter, and this is a significant linearity problem. So intermodulation product is an important parameter to consider when you are talking about non-linearity, the system level or device level at least, okay. So once we again will come to that, but a little bit of mathematics is very important here because of the fact that again I will come to the real IDVG curve that we are familiar with again, but in general if you consider this is an output and this is an input, then this is your linear term. You want the gain to be, how do I say, you want the gain to be, or the signal strength to be concentrated in this, because that is your linear term, but these are non-linear, second order, third order. If you simplify them, you get this last line here, you can see that this is your DC offset term, this is your fundamental, which means your core frequency, the frequency at which you are transmitting omega, the frequency of your desired, the frequency of your preference is omega. This is the power that the coefficient corresponding to that the fundamental frequency, which means this is the gain that you are going to get in the signal and in the fundamental frequency. This is the second harmonic. It turns out that second harmonic does not create a problem in many cases, but the third harmonic creates a lot of problems. So this is the coefficient of the third harmonic, 3 omega t. You are going to get signal power at 3 omega t, and this is the coefficient of that. So this is the gain corresponding to the third harmonic, okay. So apparently even harmonics, actually this second order harmonics kind of vanish for system with odd symmetry, and it so happens that transistors could be systems with odd symmetry, so you do not care about this so much, okay. And you can see that the amplitude goes as a cube, the amplitude goes as a square, amplitude goes as a, okay. This is actually, this a cube is smaller because omega 3 is smaller. So at nth harmonic the amplitude grows as a to the power n, which means that if your signal strength, what is a is your a cos omega t was actually the initial signal, correct. So if your a keeps increasing, which means your amplitude of the original signal keeps increasing, then a to the power n also keeps increasing. So with higher input power, the higher order harmonics become more prominent, okay. In many cases the harmonic distortion may not be important because you at much higher frequencies, omega 2, omega 3, omega, you can suppress it filter, but you have to consider the harmonics before dismissing them, because sometimes your other components in the RF block could have operations close to those frequencies, so then you will have a problem. So you have to consider them carefully before dismissing them, okay. Now I will give an example. I will not go through the math, but this is an intermodulation product distortion. So, suppose I have an unwanted signal at 850 megahertz, I have an unwanted signal at 900 megahertz. They will mix and match and they will create signals of 1750 megahertz, 50 megahertz. Okay. Now, what happens? Okay. These are desired these are desired signal. This is a mixer. Okay, this is a mixer. So, you are bringing in a signal at 850 megahertz and you are bringing a signal at 900 megahertz. This is a mixer. So, it is going to mix them signal. So, the desired output is actually 1750 megahertz. This is a desired, or it could be 50 megahertz, the subtraction of the two signal. This is desired, this is what you desire. Okay, this is you are mixing the signal. However, omega 1 and omega 2 will also create intermodulation product, which is omega 1 minus 3 omega 2, which is 1850 megahertz. This is undesired, and 1850 megahertz is so close to 1750 megahertz that you cannot filter it out. So, this is going to be difficult to filter, and 18 megahertz signal, 1850 megahertz signal is going to corrupt the 1750 megahertz signal. So, the intermodulation products could be very close to each other, that is what it means. Okay. Anyways, I already talked about gain compression, so I am not going to discuss this again further. You can read the math, the slides will be uploaded. But what I am going to tell you is that this point of 1 dB compression, I told you, where the gain compresses by 1 dB is called the 1 dB compression point. This is your input power at which the gain compresses by 1 dB. Mathematically it can, because you are losing power in the third harmonic as opposed to having everything in the fundamental frequency of omega, you can mathematically express that this point, the 1 dB compression point, can be expressed as a square root of 0.145 times the modulus of alpha 1 by alpha 3. What is alpha 1? What is alpha 1? Alpha 1 is this. Maybe I will remove this, then it becomes easier. Alpha 1 is the coefficient corresponding to the fundamental frequency, and alpha 3 is the coefficient corresponding to the third order harmonic, or the third order term, you can say the third order term. Okay. So, what does it mean? It means that to have, you want this quantity to be as high as possible, because if this quantity is as high as possible, you have a larger range over which you can operate the device fairly linearly, because your 1 dB compression point is far away. Okay. So, if you want this quantity to be as large as possible, then what it means is that alpha should be large, okay, alpha should be big, and alpha 3 should be small as possible. Okay, alpha 3 should be as small as possible. How do you physically realize that at the device level? You will see that when you talk about the output current ID as a function of input parameter, which is voltage, the gate voltage, you have GM times VGS. But if I expand the Taylor series, then this becomes the first derivative of GM dash into VGS square plus the second derivative of GM into VGS cube plus dot dot dot, you do not care. So, this GM VGS, which we typically use, is your alpha 1, and this does not matter, and this GM double dash is your alpha 3. So, in a way, the first 1 dB compression point is proportional to the square root of GM divided by the second derivative of GM, and the second derivative of the GM should be as small as possible and the GM should be as high as possible, which we know. So, this second derivative of GM should be as small as possible. This is precisely the reason why there should not be very sharp abrupt turn on or turn off, at least it should kind of gradually turn on and turn off, you can prevent that. And secondly, over the range, the input range over which you are going to operate, that input range should have as low a second derivative of transconductance as possible. The second derivative of transconductance should be as low as possible in the window. I will come to that in the next slide. Okay. So, this is very important. That is why your second derivative of GM should be small, the GM should be large for a good linearity. Okay. And this is intermodulation distortion. I already told you, if there are two unwanted signals, they can interfere and create an unwanted signal which is very much overlapping with the fundamental frequency. That is two interfering signal for intermodulation product. If there is one interfering signal and it is interfering with the design, it could have desensitization, it could have gain compression. Okay. And again, if you have a single signal, it can have harmonic distortion. So, just please keep this in mind. Okay. Again, for a intermodulation distortion products, or at a two interfering situation, if you recall this situation, these two interferes are there, no, what is going to happen is that you are going to lose out power on the third harmonic, or you cannot, I would not use the word third harmonic, you are going to lose out power on the third order term, the nonlinear term. Okay. So, this is your third order nonlinear term where the power is being lost, and this is your fundamental desired signal where you want all the power to be. At lower power levels, in the x axis is the, you can say, the power level, okay, input power level, that lower power level, and this is a log scale. So, the desired signal, which is this, it is much larger in magnitude than the undesired third order signal, but as you keep increasing the power, they will approach, they will catch up, and at one point they are going to merge. This is a very high point, you cannot experimentally measure this point, okay, it is a very high point, but you can theoretically or calculate it out based on experimental data that you have in the lower range. Okay, you can extrapolate and find out. So, this point where they are going to merge is the point where your fundamental, the power you are sending or losing, or you is transmitting at the fundamental frequency of omega is exactly equal to the power that you are losing out or transmitting in the undesired signal of 3 omega, okay, which is very bad, which is the worst case situation, So, you do not, this point should be as far away as possible in the x axis, and that will make sure that it is as far as outwards in the y axis, which means you have a larger range over which you can operate linearly. So, this point on the input side is called AIIP3, which is the input third order intermodulation product point, and the output side is called OIP3, okay, that is the output intermodulation product, the third order product that is merging here. This quantity should be, or you can quantify either IIP3 or OIP3, okay, people choose to do either. This should be as large as possible. The larger this value is, better is the device in terms of linearity, because the device allows for a larger range of input power over which the device can operate relatively linearly. It is not experimentally measured value, these are always extrapolated and extracted based on experimental value at the lower power levels or realistic power levels. Okay. Now, this point OIP3, again I have to remove the annotation here, this power, the OIP3 here, okay, or IIP3 you can say, does not matter, is actually dependent on the square root of 4 by 3 into alpha by alpha 3, which again turns out to be square root of gm by the second derivative of gm, and of course 4 by 3 is there. So, this also means that for a better or a higher IIP3 or an OIP3 value, you want to have a higher gm and a very lower gm double dash. Okay, this is very important. So, in a GaN HEMT, when we look at the gm, the second derivative of the gm should be as low as possible over the range of interest. So, what does it mean? I will come in the next slide, I will show you pictorially what it means. This is one very important aspect of linearity in the device. The second aspect is that to maintain a flat gain profile, as I told you, you also need a flat GM profile, which means if you are going to plot the GM as a function of VGS, and remember these devices are mostly depletion mode, you want, suppose this is minus 3 volt, you want the GM to stay as flat as possible over a range. However, the GM actually drops, that is a bad thing. Okay. The GM comes and then drops like that. Why does it drop? There are some hypotheses, there are some reasons, and by addressing those reasons people have been able to show fairly linear or flat GM. So, flat GM helps improve your flatness of the overall gain in the large signal output, notionally at least, as in if you have a flat GM, it helps you also achieve a flatter GM in the large signal characterization, although there are other parameters that could come into play, such as biasing condition and other things. However, the second aspect is that the second derivative of GM has to be as low as possible. So, you should not have sharp turn ons or spikes in the GM profile, especially turn on, turn off, and even otherwise. Okay. So, these two conditions, flat GM and no abruptness in GM, in the second derivative of GM, these two conditions are very useful for maintaining linearity at the device level. There are also other aspects pertaining to the linearity of device level. For instance, your capacitance CGS has a nonlinear dependence on the voltage, okay, gate drain capacitance also. So, those capacitances can vary nonlinearly. There are traps in the buffer of the gallium nitride on the surface on the interface, those traps can behave non-linearity under large voltage swings. There is heating effect also that can play a role in non-linearity, because the heating will raise the temperature will activate more traps. So there could be a non-linear play there. So there are different factors that also contribute to non-linearity. Those have to be modeled carefully so that you capture the accurate large signal behavior of the device in your device model. However, flat GM and no abruptness in double derivative of GM are very important requirements from the device point of view. Okay. So if I want to show pictorially, this is a schematic from a recently published paper. The paper's reference is given here. This is one of the first papers that is talking about the understanding of linearity from the device point of view and whether it matters at the system level. So that is a very complicated linking, by the way, and this paper is mostly simulation, but that is very useful. People are yet to show experimentally many of these things, but what this paper concludes, I will come to this picture in a while. What this paper concludes is that an excellent linearity figure of merit at the device level, which is OIP3, a gain compression, IIP3, etc. An excellent value of such linearity matrix at the device level does not necessarily translate to improving the peak linearity performance at the system level. It only helps you increase or improve the input range of your biasing of your device, okay, but it helps improve the input biasing range of your device as far as linearity is concerned, but the peak performance of the device is fairly independent of this improved linearity at the device level when you talk about the system level. This is based on the simulation studies that this paper has published. Okay. So when you look at the system, when you talk about the system level, what do I mean? Okay. So before I go to this, maybe I have to just take a small detour here, okay, because I want to say that what does it mean to have a system. So linearity is a very important in RF power amplifier for wireless communication, okay, wireless communication or maybe 5G and etc. So inherently because that's linearity is very important concern in wireless communication. Non-linearity can significantly distort and corrupt your signal. So although you are going to increase the efficiency for better battery performance, longer battery lifetime, but it is not like you can sacrifice all linearity. Linearity is very important for better signal integrity, fidelity. Okay. So wireless 5G and all this communication, wireless communication depends strongly on linearity, and today's wireless communication has a lot of digital RF in it. What does digital RF mean? You have digitally modulated RF signals. So you have digitally modulated RF signals, so you can implement many modulation schemes that you might have read about in your undergrad or postgrad electronics courses, something like QAM, quadrature amplitude modeling, modulation, phase shift keying. So there are different modulation schemes, digital modulation schemes that can be implemented on the RF domain. Okay. And so the way the system people, the people who make the power amplifier go into a board such as a front end module, a transmitter chain, a TR chain for instance, when you are actually making the transmitter transmit receive chain, when you are actually making the front end module, maybe you are making the transceiver IC, okay, those are I am talking to them as I am talking about them as a systems or a circuit people. They quantify the linearity in different matrix. They do not always use the terms like OIP3 or IIP3 or gain compression, 1 dB gain compression. These are the terminologies that device people use, but the people at the system end, they use some other matrix for linearity. For instance, they use something called EVM, error vector magnitude. It is a more complicated thing to understand, and this is not within the purview of this course, so I am not going to talk much about that and talk about that at all actually, but it is more to do with the error vectors in a constellation diagram. You understand a constellation diagram? This is a Q versus I diagram. It is a constellation diagram, the way it is a representation of the way you send the symbols in a modulation scheme. You can have a circle and you can have different points here. Essentially this angle gives you the phase and this gives you the magnitude. Okay. So different modulation schemes have this different constellation diagrams. You want to minimize the error vector, okay, and it is typically expressed as a percentage of the desired signal. Okay, that is about it. So people in the system level talk about error vector magnitude. People in the system level also talk about something called ACPR, which I very briefly mentioned in one of the previous lectures. Some companies also call it ACLR, I guess, adjacent channel power ratio, adjacent channel leakage ratio, etc. So if you have a desired signal at a frequency of omega naught, there would be undesired power that you are transmitting at close by frequencies, very close frequencies, which you do not want. So how much power you are leaking there is your this quantity, and this quantity should be as low as possible. That means you are losing out as low power as possible, and that is why it is expressed as something like say 40 dB C. C stands for center with respect to the center frequency. If you minus 40 dB C means that with respect to the center frequency, and this is very closely spaced apart, very close frequencies. Minus 40 dB is the reduction 10 to the power minus 4, it is the reduction in the power in the nearby signal lobes. The higher this value in terms of so minus 50 dB C is better than minus 40 dB C. Okay. So adjacent channel power ratio and error vector magnitude, these are some of the terms in which the systems people talk about. So the paper I had shown you here, the schematic here, this paper basically has found that the device level linearity matrix need not necessarily translate to an improved error vector magnitude or an adjacent channel power ratio at the system level. But I am sure more studies are required in this direction in terms of experimentally validating the same and experimentally understanding different nuances, because many of these things like EVM or ACPR is actually derived or studied once the device is put into the particular environment. In the when I say environment, I mean the front end chain or the transmitter chain. In that exact chain you are going to put the device and then look for EVM or ACPR. Okay. So it depends on the surrounding RF environment. Okay. So that is very important to understand here, but nevertheless people studied linearity from the device point of view, and they very much effort in improving these quantities also. Okay. At the device level. So there has to be a bridge between correlating this to the system level at in the experimental way, but that is the ongoing research. So what this image shows that this is an ideal device where it should be as linear as possible. You can see that this is as linear as possible, and if it is as linear as possible, then you get a gain which is flat, and then the derivative will look, first derivative will look like that, the second derivative will look like that, but because this was flat, so that is why this is 0 and this is 0. So within this range your double derivative of GM is 0, which is fantastic, it is great. But this is ideal in a linear device. In a real device the current does not increase linearly. So what happens is that the current has this gradual roll off, and so the GM falls off. Because the GM falls off, the first derivative looks like that, the second derivative looks like that. So within this range the second derivative GM is not very low, and that is going to impact your linearity. So what people have done in this is, I will just simply explain what this is all about. There is something called a DS approach, a derivative superposition approach. So what people do is that they can use say 4 different transistors in parallel. These 4 different transistors have 4 different threshold voltages. So what I mean is that suppose I have one device whose threshold voltage is this, another device whose threshold voltage is this, another device whose threshold voltage is this, and another device whose threshold voltage is this. Okay. So what happens now? So what happens now is that the GM for all of them looks different. So the first GM will look something like that, correct, and the second GM might look like, because it is here, so it will look my damn, the third GM might look like that, fourth GM might look like that. If you, because they are in parallel, you have to add them up to get the overall thing. So because the GM looks like this, so the GM will look like something like that. So the overall GM of the 4 devices in together will look something like that, So you are kind of getting a flat GM profile here, and not only that, you are going to minimize the second derivative also. So that is called derivative superposition. You can see that there are different threshold voltages, and while doing that you are getting a linear kind of a IDVG, and that gives you a linear or a flat GM. So this is a technique people implement at the device level to improve the linearity or the flatness at the overall the large device level. You are increasing the number of devices in a single device, you can say that. Okay. So the last thing that I will quickly discuss here is about the reason why the device can behave non-linearly, okay, or in the GM is not flat in gallium nitride HEMT. So you know that the GM in a gallium nitride HEMT, it falls off like that, right. Why does it fall off? There are 2 theories. One theory is, it says that the velocity of electrons, and this is a gate voltage. So if you go in this direction, you are looking at higher and higher 2D electron gas density. Okay. So one theory says, and it's based, the first theory is based on optical phonon scattering. Okay, optical phonon scattering. This theory says that the velocity of electrons reduces as your electron density increases as a function of 1 by square root of s, which means as you are going towards higher and higher gate bias, you are increasing the 2d electron gas density, which means your velocity is falling down, and because this velocity is falling down, your overall current is actually, the overall ID versus Vg does not go linearly like that, it goes slightly non-linear like that, and because of that it goes like square root of ns, and because your Gm is the derivative of square ID versus Vg, if you have a derivative of square root of ns by Vg, it will become 1 by square root of ns, and that is why the Gm falls off this way. So, the way to mitigate this is that they say this is a fundamental problem of 2d electron gas. In a 2d electron gas, the velocity will always go as 1 by square root of ns in a very scale device, by the way, where parasitics are minimum. This is the theory. So, they say that do not go for 2d electron gas, go for something like a smeared out or a spread out electron gas. We will not call them at a gas, but we will call it a 3d electron slab. Okay. It is like a MOSFET, it is a bulk doping. If you take a layer of gallium nitride which is bulk, say it can be some 30, 40, 50, 60 nanometer, which is n type doped, it is like a MOSFET, then you are going to mitigate this issue. But MOSFET is not good because your scattering will be too high because of the ionized impurities, right, background impurities, so your mobility will be low. So, what people do is that they do a technique which is basically to polarization grading that they use. Okay. Polarization grading means if I use a slab of AlGaN, I start from aluminum 0% or aluminum some low percent, and I keep continuously growing it to say aluminum 40%, continuously growing. This is called grading, as you know, and if you do that grading, because there is dipole associated with the polarization associated with this unit cell, because of the continuous grading you are going to get a slab of electron without any n type doping, and this has a good mobility because there is no background ionized impurity. You are getting the electrons purely because of polarization grading, but this is not 2d electron gas, this is like a polarization graded slab. By using that, people have shown that your GM can be relatively flat. Okay, great. The second theory says that your GM falls off like that usually because of a nonlinear dependence of source excess resistance. What it means is that you have a gate, you have a source, between the source and the gate is your source excess resistance. At higher current levels or higher VGS, the source excess resistance becomes a nonlinear dependence, it exhibits a nonlinear dependence, and what happens is that this becomes comparable to the actual channel resistance, and that is why the GM rolls off. The solution here would be then to ensure that this quantity is much smaller than this quantity, so that even if this quantity increases nonlinearly, it does not impact the actual channel resistance. So, the way to do it is that if you look from the top, if you have the gate like that, you do not have a single gate, you just make it a nano wire. You make it nano wire so that you have discrete like channels, and the source and the drain are like complete 2d electron gas. These are complete 2d electron gas, this is complete 2d electron gas, but below the gate you do not have 2d electron gas, below the gate you have 2d electron gas, but you have like islands, you have like nano wires. So, you are basically increasing the resistance of the channel. So, what happens is that your source excess resistance becomes much lower than the channel resistance, and the nonlinear effects kind of mitigate, and in that case also the GM could be relatively flat. Both approaches have shown that GM can be flattened out. Okay. In this approach, it is called GaN FinFET or nanowire FET. Your current density will be pretty good, but your absolute current will be low, which means to get the same absolute current, say if you want to get 1 amps of current with nanowires, you are going to need a much larger periphery of the gate. So, you are going to waste a lot of real estate, but you are going to get improved linearity. So, these are the two main theories of the GM drop off, and these have been suppressed to a large extent, but how they influence at the system level is still not done. So, with that we will conclude today's lecture as a fairly long lecture, but we have discussed in details about the linearity and specifically looking at linearity in gallium nitride transistors. And as I told you, it is a very emerging topic of ongoing research, because 5G and other wireless communication approaches, they need the market for gallium nitride power amplifier is booming, and so the necessity of having linearity without sacrificing the efficiency is also increasing the demand is increasing. That is why linearity is a very critical aspect of gallium nitride power devices today. Okay. So, with that we will conclude lecture 34 here. From next week we will start about the most common device, which is silicon. We will talk about RF silicon MOS, CMOS, and we will talk about RF silicon LDMOS. Okay. So, thank you for your time. I will see you in next week.